All right, we are starting a new chapter on quadratics, and should be interesting because first semester we were only dealing with lines, and now we're dealing with things other than lines. We're going to find out what a quadratic is. So let's start off with our very first slide here, and we can reduce this. We don't need that open. So we're going to find out how to expand squares of binomials, and we will also be using quadratic equations to solve different styles of problems. So let's move ahead. I hope you're remembering these quantities that were squared. So an x minus 4 quantity squared, a 2x plus 5 quantity squared, and the other one is just y equals kx squared, which we did during the first semester. So if those are in your memory bank, great. If not, we are going to revisit them for a very short time so that you do have some recollection of them. So let's get started. What is a quadratic? Definition of quadratic was anything whose variable is not larger than a 2, meaning a squared. So if we're talking about a quadratic, and most of ours are going to be in one variable, then we will be talking about something that looks like this: ax squared plus bx plus c. Notice, highest to lowest according to the variables. I got a second degree, then I have a first degree term. There's the second. Then I have a first degree term. We never write it, but it's understood to be a first like that. And then down here we have no variable, so therefore we have a 0 degree term. So right on down, 2, 1, 0, everything's in order. Highest to lowest according to the exponent is what we require standard form to be. Now, just as a tidbit, an extra challenge piece, something to look ahead on, if we had two variables, it would be more like this. And the spacing's off there just a little, but otherwise it looks pretty good. Ax squared plus bxy plus cy squared plus dx plus ey plus f. Now again, this one's slightly tricky, but most people see it. It again is in order from highest to lowest according to the variable, and we always use the variables in alphabetical order. So we have a x is our primary first variable, so it trumps or is more powerful than a y because alphabetically x comes before y. So right now I'm looking at, these are all my terms that just have an x in. So now I'm going to go through and I want to make sure I put them in what we call descending order. So I'm a second degree term. Question is, what am I? This one is clearly a second degree term, clearly a first degree term, clearly a first degree term, and then clearly a 0. What you have to remember about x, y, that is x is to the first, y is to the first. So really that is a second degree term when you count both of those. So that's why it gets priority and gets put in between the x squared, y squared term, because it has an x in it, which makes it a little more powerful. It is second degree, and therefore it should be in front of the y term, which is also second degree. Okay, enough of that because we are going to be spending most of our time on the one variable quadratics. All right, I'm hoping you're remembering from Algebra 1 some quantities that are squared. When we have a quantity squared, x plus y and then the quantity squared, or x minus y, the quantity squared, you had some choices. It basically means you have two of them that are exactly alike. So I'm just writing an example down here. So if I had x minus 4, the quantity squared, I could have written it as just one parenthesis with that one quantity squared, or I could have broken it up. A lot of you probably have preferred to break it up because it allows you to think of what you're going to do. What are your steps? And most of you, without me doing it, would have said, well, first times first, x squared, outsides, negative 4x, insides, negative 4x, and last times last, negative 16. Or, sorry, positive 16. So when you got that, you were looking at a 4-step process, really. And then after that, you had to collect like terms. So what we're saying is, if you did enough of those back in Algebra 1, you should have discovered there is a pattern to them. And it always works this way. So this one would eventually turn into x squared minus 8x plus 16 if we simplified, added the extra step to simplifying. And we're saying up here is all quantities that have an addition sign in them will be x squared plus 2xy plus y squared. Every single time, no matter what the combinations are in front of the x's, in front of the y's, you're going to do that math. If it's an x minus y combination, then there's only going to be one real difference. Look at it. The terms appear to be the same. The signs at this end are the same. The only difference is right here. So if we're going to get the same answer, whether it's a plus or a minus, we just have to remember the process, what you're really doing. And I'll say it in words, and some of you will want to write it down like I have it here. You could FOIL, but remember what we just said. FOIL is like 1, 2, 3, 4 steps because of the multiplying. So 1, 2, 3, 4 steps. Then collecting like terms was like a 5th step. So there were some things you had to do. Now we're saying we want you to think of it in a slightly different way. And that different way goes like this. We want you to take whatever that first term is and square it. Then we want you to take the product of the two terms. The two terms are what's inside the parentheses. So these two things, what's ever there. If there's numbers, if there's variables, go ahead and multiply them. That's what product means. So x times y is xy. But then it says, and double it. So if I have an xy and I want to double it, when you double anything, you times it by 2. So we'd have 2xy. And that's what you're seeing in the middle terms up here. And then last but not least, it says square the second or the last term. So our last term in both cases is a y. Square that, y times y squared, and you should be done. So we'll put a new one up here. We'll put a couple. But let's start with, let's just do the quantity of x plus 5, that quantity squared. Now we're not going to FOIL it. We're not going to rewrite it. We are just going to use our shortcut math. Here we go. Look at your two terms. You've got an x and a 5. If you want to think of it as a 1x, that's great. It's not going to do any harm. Here we go. Square the first term. You would get x squared. Then add, take the product of the two terms. 5 times x, 5x, doubled, 10x becomes the middle term. And square the second or last term. We have a 5, so 5 times 5 squared. 5 times 5 is 5 squared, or 25. And our final answer is x squared plus 10x plus 25. 3 steps. You wrote the answer. You didn't have that extra step. You didn't have any combining like terms. Everything was done. So this is slightly quicker than FOILing. When can it be used? Only when you have a quantity squared, a parenthesis that is squared. Let's do one with numbers because they're always a little trickier. Let's go 2x minus 3y, that quantity squared. We're going to do the exact same thing. Here we go. Square the first term. 2x times 2x, 4x squared. Take the product of the two terms, the numbers and the variables. 6xy, and it was a negative, but double it, that would make it 12xy. And then square the second or the last term. A negative 3y times a negative 3y is a positive 9y squared. So our final answer again in 3 quick and easy steps. 4x squared minus 12xy plus 9y squared. The nice part, it's in descending order. There's no collecting like terms. Everything's there. And it's called the binomial square theorem. Okay? So, in the book, I believe you read about a swimming pool situation. Well, ours is going to be a little different here. let's assume that we are senior year. We want to put up a nice bulletin board, little class project, and maybe have the cutest baby contest. So this bulletin board that we have to display these pictures on measures 8 by 3. So let's add that to our drawing. We've got 8 feet by 3 feet. Okay. From there, more information is that the decorating committee plans to put a border of the school colors all around the interior edge of the bulletin board. So like the bulletin boards that you have in class here. All right, little extra border, color things up. The border will be b inches wide. We want to write an expression for the area that is available for the pictures and expand the expression using our distributive property. So right now we got one more thing we really need to do. Obviously, I've got some pseudo pictures up here, but what that said was there's going to be some kind of border, and that border is going to be sitting here, which means that's space taken away from hanging the pictures. Now, we don't know how wide they're going to decide on yet, but we know that they just told us we're going to assume that it's b in width. Okay, so an unknown value. All right, and then we'll have the room to hang the baby pictures. Okay, so we want the area of the space where the pictures can be hung, not the area where the border is at. So let's go back and say, okay, wait a minute. We have a rectangle. That's the outside of our board is the blue. We have the yellow, which represents the space the border takes up. And we needed to basically find out what's left. So here we go. If 8 was our original length, and we have this edge and this piece that are gone from it, because it's now only the edge in yellow, we would probably have to say 8 in length and then take away, it's shortened because we took away 1b down there, 1b down here, so we have an 8 minus 2b is really this dotted line length that we have. And since we know area is length times width, we now need to do the same thing on our width expression. So here we go. Look at our old width. Our old width was 3. We can see it marked here. But in essence, we took away this little piece off the end and this little piece off of this end. So we used to be 3 in length, and if we took 2 dimensions that were b in length off each of them, we'd have 3 minus 2b. Now, if you look at those carefully, they are binomials. They are not exactly alike, so we can't use that square binomial theorem that we had in the last one. We are going to have to do our foiling. So here we go. First times first. 8 times 3 is 24. Outsides, negative 16b. Insides, negative 6b. And last times last, positive 4b squared. Combine like terms. I see some b's in the middle that are alike. Let's put this in order. And we would put 4b squared first, our negative 22b in the middle, and our plus 24 on the outside. So that would represent the area that we would have for arranging the baby pictures. As soon as whoever's in charge of this committee or whoever's in charge of the group, as soon as they decide how wide the border is, whether it's 2 inches, 3 inches, 4 inches, 5 inches, or more, then we could stick that value back into our equation and know how much area we're working for. So we could really, choose how many pictures we wanted, what size they really need to be, things like that. So that's what you have for this one. And you should be good to go and work on these. The only reminder I want to say about this, if you look back at it, forget about it being a bulletin board. It started out as a rectangle, which is length times width. And then once we had that other piece added to it, we could just say it was a rectangle inside of a rectangle. And so we are dealing with shapes. We're not necessarily always thinking of it as, oh, this is a bulletin board or for a swimming pool or a sidewalk like the one in the book. Okay? So put yourself in context of what it is shape-wise, and I think that'll make it easier for some of you to work through. So that's all we have for this first section. Bring any questions you have to class.